Good morning, everybody. Today we are with Hans Dekker. Good morning, Hans. How are you?
Hello, Laurent. Good morning.
Second part of our basic training concerning the compression packing. Last time we saw the fundamental. We saw the main criteria concerning a good packing. And today, in the second part, what are we going to see?
Yeah, the second part, Laurent, we are going to talk about the different manufacturing methods and about the different materials that are used to make compression packing. So,
okay,
if you're okay with it, I will start with the continuation of this presentation. So we're going to talk first about manufacturing methods. How is packing produced? So, and to start that off, I'm gonna actually start off with a video because we have very nice videos in Chesterton where we talk about this. So let me just start the video and then we talk further.
We live in a world of fluids, where flow is often controlled by the twist of a knob. Bringing the fluid to this position, though, requires large amounts of piping construction, pumping machinery, and controlling devices. The movement of the fluid is managed by pumps, machines that transfer a fluid from a source or container through the pipes to a receiver or another container. Centrifugal pumps are the most common systems used for this operation. The essential parts of a centrifugal pump are the impeller, or rotating member, and the case or housing surrounding the rotating member. Velocity is imparted to the fluid by rotating the impeller at high speeds. A series of valves control the flow of the pumped fluid. By opening, closing, or obstructing internal ports or passageways, direction and flow are regulated. Pumps and valves require the use of a fluid sealing device. Our focus will be directed to the sealing method referred to as mechanical packing. Rings of pliable material are installed around the shaft or stem of pumps and valves to contain process fluids and eliminate fluid loss. The objective of this video program is to show how mechanical packing is manufactured.
Packing is used in pumps, packing is used in valves, and now I'm going to show the second video about the manufacturing.
Spools of yarn are received from an approved supplier. In the winding area, each spool is inspected, logged in, and readied for use. The spool is placed on a rotating rod and pulled through a lubrication holding tank, coating the yarn and sealing it against the environment. The coated yarn is then rewound onto metal bobbins in preparation for the actual manufacturing process. From the winding room, the bobbins are taken to the braiding area, where they will be placed onto the rows of the specially designed braiding unit. Each machine in the ventilated housing unit is programmed to interwind the separate yarns to a specified cross-sectional dimension. Compression packings are made in a variety of shapes, sizes, constructions, and from numerous types of materials.
So there we saw an introduction for the materials used, and this was particular about braided packing. So let's look a little bit further about that.
Just a question is okay. Later.
Precision squaring of the packing is necessary. Squareness ensures that the packings will fit snugly against each other when they are installed as ring sets in a pump or valve. The specially designed machinery provides consistent size and density to the packing lengths. During the course of this squaring operation, the lengths will be measured with a vernier caliper to confirm the cross-sectional sizing. The squared lengths are then wound onto a spool in preparation for packaging. This wrapping method will eliminate possible damage to the packing material during shipment, use, and inventory storage by the end user. Once the coiling is completed, the packing is cut away from the lengths and stapled down. The spool is then weighed and ready for final packaging. The spool will be placed in a box containing product information and installation instructions.
Laurent, you wanted to ask something just when the video started?
Yes, they are quite old video. This is still the same process, right? More or less. Do we use exactly the same machine, or do we have different kind of machine to braid packing?
We have, of course, some newer machines, and some of the measuring methods that you saw, they are currently a little bit different, more automated, but okay. In principle this is all pretty much the same manufacturing methods that you saw in the video. Okay, so let me continue a little bit. The video that you saw, that was about manufacturing of packing, and it was in particular about the manufacturing of braided packing. So, and braiding is actually a manufacturing method that is predominantly used for compression packing. And just to look into braiding, there are a different number of braids that are used. So, and I will concentrate here on just two of them, the ones that we mostly use for our packings. So the first braiding type is square braid, and actually square braid is used for materials that are a little bit weaker, and it is used as well for somewhat smaller cross section. But it is effectively a braiding method that braids fibers into like a square format that fits very nicely in a stuffing box that we basically talk about in the first session. Square braid you can recognize by looking at the side of the packing, and you basically see two tracks when you look at the packing. If you look here on the pictures as well, you see two tracks that are visible, and that in contradiction to the next type of braid we're going to discuss, where there are 3 or more of these tracks. So one thing that I have to mention as well is that, and that we actually saw in the video as well, after the braiding, the braided packing is actually run through some rolls to make it actually more square and to exactly size it to the required dimension. You saw that very clearly in the video as well, with the rolls.
Okay.
So the next braid we're gonna show is interbraid. So interbraid, we actually recognize, and we can see that there are 3 of these tracks when we look at the side of the packing. It's not so good visible on the picture here, but here we see basically 1, 2, 3 of these lines of these braids. So interbraid is actually braid where thinner yarns can be used, and it produces actually a very tight and dense braid. So it actually produces a stiffer packing, a more square packing, and as well a denser and tighter, less less porous braid, to say as such. So another manufacturing method for compression packing is die forming. And die forming is used to produce, for example, flexible graphite rings. So, and this die forming is done in basically a press, under a press with a form. And this form consists of a core, and the core determines the ID of the packing ring. It has a shell, which determines the OD of the packing ring. There's a pusher and there's a bottom base here. So, and if I look at the next picture, what you can actually see is that the packing material is put into the form and then a load is applied on top of the tool. So in this way you can produce a packing that has very good sizing, so it has a very accurate dimensioning. It has a controlled density, and as well it has a controlled height. So and so as I mentioned, this manufacturing method can be used to make flexible graphite rings, but it is actually used as well to make braided packing to die formed rings that have a more accurate size and a more controlled density.
A question, Hans. When you show here the sealing material, does it mean that you use the square interbraid packing that we have seen before, or it's another thinning material with manufacturing with another method?
Yeah, we can use two things. We can use flexible graphite in the form of a flexible graphite tape, and this is rolled up into a roll, put in the form, and then pressure is applied to make a dense ring. The second thing that you can use is a cut braided packing ring that you put in the form, then you apply pressure, and then you actually get as well a nicely compressed packing ring. All right.
You don't have a risk to put away the internal lubricant, or we've seen last time that we have.
That is basically not an issue. What you basically do with this die forming is you make a packing ring that has the exact dimensions of the stuffing box that will be in the pump or in the valve. And what you do as well is when you think about when you install packing in, for example, a valve or a pump, and you cut it straight from a spool, then you basically install the rings, and then you have to start compressing the packing in the pump.
Yep.
This whole process becomes easier when you use die formed rings because they have a higher density, so some of the pre-compression that you would do in the equipment itself, like the pump or the valve, is already done in the factory.
Yeah, okay. Okay.
It actually saves time.
Yeah.
All right, so let's look at the components that are used in packing. So packing, and specifically braided packing, consists of fibers, and fibers can either be natural fibers or they can be synthetic fibers. So of course, in the past a lot of natural fibers were used, but modern packings, they contain synthetic fibers that have been manufactured and developed specifically for the application. As well, the braided packing contains lubricants. So there are lubricants that are completely integrated in the structure of the packing. In the videos we saw that the yarns that are used in production, they were basically pulled through a bath of lubricants, and that before the packing was actually braided. And these lubricants, they actually are completely included in the structure. What you have as well are break-in lubricants, and break-in lubricants you can see very well on this picture here on the right. That is the packing or the lubricant that is applied to the packing after it has been braided. So after the braiding has been taken place, some lubricant is put on the outside of the packing that actually assists for the first 15 minutes of running of the packing, so it can nicely conform into the packing in the stuffing box and gives the necessary lubrication for the first 10-15 minutes of operation. So the other thing that is added into packing are blocking agents. And blocking agents, basically, if we think about a packing, specifically a packing that is braided, you have this braided structure which is like a sort of a net of fibers. So obviously these little holes that are in the structure of the braid, they need to be filled up with something. And that is being done with blocking agents. Now actually the function of blocking agent and lubrication is actually many times done by the same components. So lubricants can actually act as blocking agents as well. So, and the last thing that is sometimes being added are corrosion inhibitors, and this is specifically for graphite, and we're going to talk about that in a minute a little bit. Graphite has some specific issues, and for that corrosion inhibitors are added to a packing material.
Hans, you talk about lubricant and blocking agent.
Yes.
I mean, we understand that one is for the lubrication, okay? And you explained that very well, and we saw in the movie that it can be built-in or break-in. But blocking agent means that we have to block something. What is the function really of the blocking agent? Is a block what kind of thing they can block?
What are they blocking? Yeah, we saw in the first sessions that we did, we saw that one of the functions of a packing has to be that it's non-porous.
Yes.
So, and I always like to give the example of the old sock. I could use my sock as a piece of packing to seal a pump. So, however, my sock is pretty porous. Water would go through it. So I need to put something in my sock to actually block the fluid that I'm sealing.
To fill the
gap. And you could imagine that if I put my sock into a stuffing box of a pump, the water would go straight through it. Now imagine that I take my sock and I take some grease and I completely fill this sock with grease, and then I use it as a packing. Well, this grease actually does two things. It reduces the friction of my sock on the shaft, and as well, it will stop water from going through the fabric.
It's a barrage. Okay, barrier.
It becomes like a barrier.
Okay, good.
All right.
Thank you.
So fibers. Let's talk about fibers. When I talk about fibers talked about fibers before. There are two types of fibers. There are natural fibers and synthetic fibers. So natural fibers, they can be either vegetable fibers, such as cotton, for example, or flax, or hemp. They can be animal fibers, like wool, for example. And they can be mineral fibers. And mineral fibers are, for example, asbestos. It's a mineral fiber, but it's a natural fiber. So in general, animal fibers are not used so much for compression packing. vegetable fibers are. Mineral fibers such as asbestos is pretty much banned. But vegetable fibers are still pretty much used, and particularly in cheaper types of packing. And there are some problems with it. They're pretty soft. The temperature range is not very high. The strength is not very high. Thermal properties are not very high. The friction coefficient on the shaft is not pretty good, and as well the chemical compatibility of natural fibers, when I talk about vegetable fibers, are pretty poor. Actually, the chemical compatibility of asbestos was very, very good, but as I said, this is pretty much banned in the entire world, so that's generally not used anymore. So there are as well synthetic fibers. Examples of that are glass fibers, aramid fibers, acrylic fibers, PTFE fibers, and carbon and graphite type fibers. And the advantage of synthetic fibers is of course that they are manufactured in a factory, and properties can be controlled very well, specifically for the requirements that we need. In the first session we talked about issues. We talked about how you can solve these issues, solutions. So actually, for example, strength was one of the requirements for mechanical packing. So if we manufacture a synthetic fiber, we can particularly focus on strength to manufacture the fiber that we need. So, and let's now look into a little video as well that we have again about fibers, so we can explain that a little bit further.
Packing manufacturers have also found new materials to create packing that can achieve superior performance in modern equipment. Researchers analyzed many natural and man-made compounds before discovering the best fiber materials. Materials like aramid and glass, with extremely high tensile strengths to handle high pressures and fast shaft speeds. And polytetrafluoroethylene, or PTFE, with its high resistance to chemicals and heat for sealing a wide range of corrosive fluids. The latest generation of fiber materials are carbon and graphite, with wide chemical resistance, high temperature capability, high tensile strength, and low coefficient of friction, all the physical characteristics of ideal packing fibers.
Oh, so okay, so that was a little fibers. So let's now continue with the presentation. So let's first take a look at one type of synthetic fiber, which is aramid. And aramid actually comes into two groups. First of all, we have para-aramid, and para-aramid is known under the trade name, for example, of Kevlar. So, and the big property, big advantage of Kevlar is of course that it is very, very strong. If you look at the ratio between strength and weight, Kevlar is much stronger than steel. And this is the specific reason that it's being used in compression packing, because it can create a packing with para-aramid. You can create a packing that is very, very wear resistant and very, very strong. So that's the reason that it's used. The other aramid type that is used is meta-aramid, and this meta-aramid is known in the market under the trade name of Nomex. And Nomex is the material that is used in, for example, race suits, and is known for its temperature resistance. So pH range of Kevlar is actually not as high as the chemical resistance of meta-aramid or Nomex. So this is about 3 to 11, and this is about 1 to 13. So, so this heat resistance and the chemical compatibility makes meta-aramid actually a very nice fiber to use, because meta-aramid is not so strong as para-aramid, but it still has pretty high tensile strength. Okay, the other yarn that is very much used in compression packings is carbon and graphite yarns. So carbon yarns and graphite yarns, they are produced by taking a pan fiber, which is a synthetic fiber, putting it in an autoclave, so heating it to very, very high temperature without the presence of oxygen, and in that way this yarn is being carbonized into a carbon or graphite yarn. What is the difference between a carbon and a graphite? Carbon has a purity up to 95% of C carbon atoms, and graphite is much purer. It is higher than 95%. So the other type of graphite that we have is expanded graphite, and expanded graphite is, for example, used to make these die-formed rings, and as well used to make braided packings. So let's look at carbon and graphite yarns. The characteristics of graphite and carbon in general is it's very high temperature resistance, and it has a very, very good chemical resistance. So it actually has a chemical resistance of, it can withstand the whole pH range of 0 to 14. The only exception is some strong oxidizing agents that is not resistant to. So carbon and graphite yarns are a carbonized fiber made from a pan synthetic yarn. And the characteristic is that it has very, very high strength. And because it has very high strength, it's easy to braid. But unfortunately, as such, it doesn't have very good sealing properties. So you're going to have to add something in that yarn to make it seal well. So the other
sorry, you say just the last point was it's a poor lubrication property, but by definition the graphite has in essence natural lubricant, isn't it?
Yes. However, if you talk about a carbon yarn,
yes,
it is, because of its strength, it can be as well very a little bit abrasive. But it's more the blocking agents that I'm talking about there. If you make a packing from purely a carbon yarn, you need to put something in there to make it seal better. So if we talk about expanded graphite, or as well referred to as flexible graphite, this is made by taking graphite that comes out of a mine, treating it with very strong acid, and then it starts to create these graphite flakes that are then used to make packings and gaskets. So these graphite flakes, they are basically used in a calendaring process to make graphite foil. So and this graphite foil is then used to make gaskets, or to cut into strips and to convert into either a yarn or a die-formed ring. Here on the right you can see perfectly an example of a die-formed packing that is made of flexible graphite tape. So this is not a braided packing. This packing is made by taking flexible graphite tape and compressing it in a die. So
if I understand correctly, to summarize, before we talk about the yarn, graphite yarn with a carbon and the graphite standard graphite packing, and here in fact we talk about flake, and in this case we pressurize all the flake together, we create a kind of a solid block, right? I'm sorry to use this trivial funny term, but in fact we put all this flake together, we compress, it's a block, and after with a die form we create the different rings. I understood correctly?
Yes, you understand that correctly. So it's actually, you take this graphite tape and press it into a ring. In this particular picture, you can see that this graphite ring has been split. So this has been cut. So you can actually open it a little bit and install it over a shaft. But we do supply these as well non-cut, so as a solid ring. So the advantage of expanded graphite is that it is a pretty soft material. So it can actually adapt itself very well to the shape of a stuffing box. And because of this, and because of the fact that it can be compressed and condensed pretty well, it has pretty good sealing properties, in particular for media such as steam or fluids. Soft, good adaptability, and as well it's non-abrasive. So this is a soft material. It's actually auto-lubricating, as you mentioned before. Graphite has very good low friction. But unfortunately, because it is very soft, it has a very low strength. So it actually, if the gap of the stuffing box is a little bit too big, it actually can extrude pretty easily. So that is the problem with that. As well, because the material is soft and it's not very strong, it's very hard to braid as well. So, and the solution for that is to combine this flexible graphite with other materials. For example, to combine flexible graphite with carbon yarns or with metal wire. And these are examples of what's being done in the packing range of Chesterton. So what we do is we take flexible graphite and we improve the packing performance by actually combining different materials. So we have, for example, our style 1600, which is particularly used in valves, where we take a expanded graphite yarn and we put like an inconel, which is a metal reinforcement around it to improve its extrusion properties and to improve its pressure resistance. Another
it's like a net finally that you put the fibers inside, and we have the net, and the net avoids the fibers to disappear or to okay.
And the other example is where we take a expanded graphite yarn and we actually reinforce the packing with carbon yarns. So in this case you can see that there are some spots here that are a little bit darker. That's actually where the carbon yarns are located to improve the pressure resistance of the packing. Alright, so another example of a synthetic fiber is PTFE. So PTFE stands for polytetrafluoroethylene, as well known on the market as Teflon. And when we talk about Teflon, we immediately think about its low friction, coefficient of friction. And we see this, for example, in the pans that are coated with a Teflon layer, where your fried egg can slide so nicely on this Teflon layer. That's actually the low friction of the Teflon there. The other property of Teflon is its excellent chemical resistance. So it has a very good chemical resistance. It has, just like graphite, a chemical resistance for pH range of 0 to 14. But where graphite is not resistant to some very strong oxidizing agents, PTFE has better resistance to that type of chemical, so it can be used practically over the whole range of chemicals that are out there. The only drawback that it has in comparison with graphite, for example, is the temperature resistance that is only up to 260 degrees C. PTFE, just like most plastics, suffer unfortunately from another problem, which is called cold flow or creep. So what happens when we actually put a weight on a wire or a rod of Teflon, it initially holds that weight, but what it actually does is over a period of time, it starts to flow, it starts to cold flow. And this actually happens when you put a gasket made of PTFE between flanges. It starts to cold flow and loses the stress on the flanges. And as well, if you put pure PTFE into a stuffing box, it as well starts to lose volume. It starts to extrude very, very slowly because it suffers of this cold flow problem. There are some remedies for this. For example, there are drawn PTFE fibers where basically PTFE as a plastic is taken and it's already pre-stretched and to improve its strength. So what actually happens is the molecules get orientated in a certain way and it improves its creep resistance. What can be done as well is that PTFE is expanded, so what we call this expanded PTFE or ePTFE. And ePTFE goes as well through a manufacturing process that stretches it and gives it some heat treatment to improve strength and creep resistance. Okay, besides fibers, there are some other components in packing, which are lubricants, blocking agents, and corrosion inhibitors. And for that, I'm actually going to show a short video again that talks about this.
There are two categories of essential lubricants used in mechanical packings. Break-in lubricants provide protection against excessive heat buildup until the packing becomes pliable and seated. Built-in lubricants serve as blocking agents to decrease packing porosity and provide some resiliency. Some common lubricants used for these purposes are Teflon suspensoid, molybdenum disulfide, graphite powder, petroleum oils, and silicone fluids.
You could see that there are different materials that are used. They are like oil type materials. But what you could see as well is that PTFE is actually used as well as a lubricant in other type of fibers. So what happens is that you take like a PTFE particles, which are very, very fine. They are basically suspended in water, and before braiding or after braiding, the fiber or the packing is pulled through this bath of PTFE, and the PTFE actually incorporates itself in the fiber or the braided packing.
In this case, we cover the packing with.
Yeah, you basically cover either the yarn or the fibers or the packing with PTFE.
Okay. Okay.
So lubricants, what they actually do is they increase the speed capability of the packing, and they can make up approximately 40% of the volume depending on the packing. So actually a pretty high percentage of the actual volume can actually be taken up by lubricants. So there are two main types of lubricants. First type is break-in lubricants. That's the packing that you saw in the beginning of the last video, where a braided packing is actually pulled through a bed of lubricant, and this lubricant basically stays on the outside of the packing. So protection against excessive heat buildup, specifically in the beginning. and it's referred to as well sometimes as a sacrificial lubricant. And then we have built-in lubricants, and they basically provide continuous lubrication. So that's the lubricant that is contained in every single fiber in the structure of the packing. And that is the lubricant that basically gives sealing during the entire life of the packing. So when you squeeze, when you compress packing further, this lubricant releases itself and becomes available to provide low friction. And these built-in lubricants, they act as a blocking agent. And what the built-in lubricants do as well is they make sure that the individual fibers, they slide better over each other, so it actually improves the resiliency of the packing itself.
It's possible to have a break-in and built-in lubricant?
Yes. Most packings, they have
most technique.
Yeah, they have a built-in lubricant and a break-in lubricant. Okay. And break-in lubricants are specifically used for dynamic applications. In valve packing, you don't see. Well, in valve packing in general, you don't need lubricants. What you need is blocking agents. So specifically for pump packings, you see these break-in lubricants.
Yeah.
Okay, another thing that sometimes is added to packings, and specifically to graphite packings, is to avoid a phenomenon that occurs when you install graphite packing into a stuffing box. And that problem has to do with the fact that when you take a graphite and a steel, in essence what you create is a battery. So to create a battery, what you need is an anode and a cathode and an electrolyte. An electrolyte is a sort of a fluid, like a battery fluid. So when you put a very cathodic material with an anodic material, you create a battery. So what we can see now is that stainless steel is somewhat in the middle of the scale, but what you can see as well is that graphite is much more on the cathodic side of the scale. So if you take a stainless steel stem, such as here, and you put a graphite packing around it, and you add an electrolyte in the form, for example, of hydrotest water, you make this wet, what you create is a battery. So, and what happens is the anode starts to sacrifice itself for the cathode, in this case the graphite, so what you get is these little holes in your stem, which is known as well as pitting corrosion. So, and to avoid that phenomenon, packing manufacturers put corrosion inhibitors in their packing. So if you look at the previous page, you see, for example, that zinc is completely on the far end of the anodic scale, so it's much more anodic than stainless steel. So what happens is some packing manufacturers put zinc powder in their packings, and what actually happens then is the zinc starts to sacrifice itself before the stainless steel stem does. Unfortunately, and this zinc powder is called an active corrosion inhibitor. Unfortunately, it sacrifices itself, and the life of this corrosion inhibitor is relatively short. So what Chesterton actually does is we put passive corrosion inhibitors in our packings. So the passive corrosion inhibitors, they do not sacrifice themselves, and what it actually does is create some barrier, like an immune barrier on the stem to stop this corrosion effect. And because it does not sacrifice itself, it is very long lasting. So, and what Chesterton actually puts in their packing is molybdate salts. That is an example of a passive corrosion inhibitor. Alright, so that is basically the end of this session of the level 1 packing course. And next time we're going to continue and we're going to talk about how is packing selected. So how do you select the packing? And as well we're going to talk about the different types of packing that Chesterton has. So we're going to talk about the core program of packings in the next session.
Excellent. Okay, then see you next time. Bye bye, Hans.
Thank you, Laurent.
Bye bye.
See you.